So it's my pleasure to introduce Professor Jeff Long. He's actually a longtime collaborator of mine and Ben Harvey's. We've worked together in the field of molecular magnetism for, I think, 8-9 years now. So it's been very productive. It's been great working with Jeff. So Jeff is the Judson King Distinguished Professor of Chemistry and many other things at UC Berkeley. He's also a, let's see here, director of the Baker Hughes Institute for Decarbonization Materials at Berkeley as well, and a faculty senior scientist in the Materials Science Division at Lawrence Berkeley National Labs. He served as the chair of the Division of Inorganic Chemistry at ACS, and he is a founding associate editor of the journal Chemical Science. He's also co-founded 2 companies, Mosaic Materials and ChemFinity, and is producing materials for selective removal of critical metal ions from aqueous sources. He's got over 400 publications with 110,000 or more citations. He has some recent awards, including the ENnie Award Energy Transition Prize, and also the Albert Cotton Award in Synthetic Inorganic Chemistry. He got his PhD at Harvard and started at Berkeley in 1997, I believe. So it's my pleasure to introduce Professor Jeff Long.
All right, thanks. Thanks, Randall. And it's a real pleasure to visit China Lake for the first time and see what's going on here, particularly since we've been having this very close collaboration with Randall and Ben Harvey for so many years. So I was very impressed to see where Randall makes all these amazing molecules. And I just want to show off an example of the kind of molecules that he's been able to make that have never been seen before. This is a graphene nanoflake. This is a crystal structure for the first time of this C78 piece of graphene that's sandwiched between 2 pairs of lanthanide ions, dysprosium ions. And this is not one of them, but Randall has made the best single molecule magnets in terms of operating temperatures on the planet. So molecules that behave individually like a magnet and have a memory effect. But I'm not going to talk about that today. Instead, I'm going to talk about designing porous materials for separation. So I changed my title a little bit and broadened it. Much of the talk will be metal organic frameworks that are designed for efficient CO2 separations. And then towards the end, I'll talk about porous network polymers that can be used for recycling metals from your devices or mining of metals. And the reason we're interested in these kinds of materials is that we spend a huge amount of energy on separating molecules and metals. Something like 10 to 15% of global energy consumption goes towards separations, and that's tied to 10 to 15% of our CO2 emissions. And the largest contribution are large-scale industrial gas separations and separations of metals in mining operations. And so I'll address both of those areas. But our goal is to really design new porous materials that can enable separations of these molecules to be done in a porous solid via an adsorptive or membrane-based separation. And for this talk, I'll only focus on adsorptive separations. And so what we're making here are porous solid sponges that can soak up large quantities of a target molecule selectively. And you may have seen there was a Nobel Prize announced in this area recently for the discovery of metal organic frameworks. Over the last 10 to 20 years, there's been a revolution in chemists learning how to build, using molecular design principles, porous solids. And these porous solids can act like sponges, soaking up large quantities of a gas or a specific metal. And so broadly speaking, these can be classified into these three groups. At the left, you see an example of a metal organic framework. In the middle, covalent organic frameworks. And at the right are porous aromatic frameworks. And there are differences in these. All of these have molecular design possibilities. But metal organic frameworks are highly crystalline materials with perfect discrete pore sizes. Covalent organic frameworks are usually less easily crystallized. And then porous aromatic frameworks that are built up of only very strong carbon-carbon bonds, these tend to be amorphous network solids. But there is an advantage to the amorphous network solids, or PAFs, in that these are incredibly chemically robust. These can tolerate strong acid or strong base. So you can expose these to 6 molar acid and there's no problem with degradation of the material, whereas that is not true of COFs or MOFs. And so that's going to be an advantage if you're trying to separate metals from an acidic waste solution. So just to introduce metal organic frameworks, these are network solids built up of organic linkers connecting metal centers into a 3D porous architecture. And these materials can have the highest surface areas of any known materials. These can be up near 8,000 meters squared per gram. And this is important, two things that are important about MOFs. One, we have incredible synthetic control over designing the pore structure. We can adjust the pore size, the pore shape, the surface functionality, what incoming molecule we'll see on the surface of the material. And then secondly, high surface area. High surface area means that if we have a surface site that's selective for binding one type of molecule, then you can have a material that's selective and can take up a huge capacity of those materials. You have a high density of those binding sites. So for separation capacity can be incredibly important for efficiency. And so for designing a MOF or gas separation, you want to identify some chemical mechanism whereby a target molecule in a mixture of molecules will be attracted to the MOF surface. And once you have that chemical mechanism of attraction, you want to design the MOF so that you have a high density of those sites in the material without limiting kinetics, without limiting diffusion of incoming and outgoing molecules. So you need to retain some porosity. Okay, so that's what we do. We try to do MOFs for targeting a particular molecule in a particular mixture under particular conditions. And the simplest way you would use these materials would be to fill a column with some form of the MOF. And in one end, you're going to bring in the mixture of gas molecules. And if you've done your job right as a chemist, only one type of molecule in the mixture, the target molecule, will stick to the MOF. Everything else comes out the other end in purified form. At some point, you're going to completely saturate all the binding sites in your MOF in the bed. And then you're going to put in energy, either raise the temperature or drop the pressure. And that will release the bound molecules in pure form, and then you'll start again. So these materials need to survive adsorption and desorption thousands and millions and even millions of times, ideally. And pretty much any porous solid that you would put into that type of bed has this type of response to a gas pressure. This is called a Langmuir adsorption isotherm. But under equilibrium conditions, the Langmuir isotherm, if you increase the pressure of gas, you'll see a steep uptake and then saturation as you coat the surface. And that isotherm shape is not ideal for an efficient separation because you're going to load up with the molecules at whatever partial pressure they are in your incoming mixture. You're going to absorb those into your material. And then to desorb, the step where you release the molecules in pure form, you're going to have to either go to very high temperatures because that Langmuir steep isotherm only gradually loses steepness as you raise the temperature, or very deep vacuum to get the molecules off. And so if you were just trying to think about response to a gas pressure, what I like to have for an efficient separation, you would not come up with this Langmuir isotherm that almost all porous solids show. You might instead come up with something that looks like this, where you have a sharp step, a sudden transition at a particular pressure and temperature. You go from no uptake of the molecules to filling your material with the molecules. This vertical switch-like response is due to some cooperative adsorption behavior. And so you can create step-shaped adsorption isotherms in materials by a variety of ways, but we want to do it in a chemically selective way. And the advantage of this will be, if you have that sharp step, you can swing between fully loaded with molecules or to fully unloaded with either a small pressure change or a modest temperature increase. So we'd like to create these sharp steps in a chemically selective way, and this is something that nature knows how to do. So a lot of what you're going to see today is taking inspiration either from enzymes in nature or chemistry in molecular chemistry in a flask. And so if you've learned about cooperative adsorption or cooperative binding, very likely you learned about it in the context of hemoglobin. So hemoglobin is this amazing molecule. It has 4 iron heme sites. When oxygen binds at one of those sites, there's a rearrangement of the protein backbone that opens up the other 3 heme sites for binding oxygen. So hemoglobin will simultaneously bind or release 4 oxygen molecules at a time. And that leads to not a Langmuir response, but a step-shaped response. This is very clever because it's our way, it's nature's way of swinging oxygen on and off the molecule within a very narrow pressure range. This is important for your livelihood. And so it's also chemically selective. Only the oxygen binds to the iron heme via electron or charge transfer. So biochemists have known for over a century now how to understand, a simple way of understanding this kind of response. And it's through what's called the Hill equation. And the idea is that if you have some, say, enzyme with many receptors, some reactions take not just one molecule, one L molecule to do the reaction, but a collection of N of those molecules. So here N is the order of the reaction. And associated with this equilibrium is an equilibrium constant. And the Hill equation is simply giving the occupancy of the receptor sites, theta, by that simple expression. And important in that expression is this exponent n. N here is the reaction order for whatever's binding. And we're going to be dealing with pressures. So here's the same Hill equation in terms of pressures. Again, n is the exponent. How many molecules does it take to drive the reaction? And so let's look at some values of n. If n equals 1, this is non-cooperative behavior, and you get a Langmuir isotherm. If we increase n to 2, you see a very shallow step starting to emerge. At 4, it's a little sharper. At 10, it's much more prominent. So we'd like to design systems where n is very large, and we have specific cooperative binding. And so if you take, for example, this data under these conditions for hemoglobin and use the Hill equation, you get from that n equals 3.7, very close to 4, which is quite satisfying. And so we're going to apply this in modeling some of our gas uptake in the MOFs. I'll show you. And nobody understood that you could do this kind of thing in a dense way in a porous solid until we serendipitously discovered that we could do it not with oxygen, but with carbon dioxide. And we were doing it in the interest of trying to do CO2 separations efficiently. So this is an example of one of the large-scale carbon capture operations that's ongoing on the planet. There are quite a few. This is attached to the Petronova power plant outside of Houston. And what you're seeing is just the carbon capture unit. It's enormous. I don't know if you can see in the background, there's rail cars of coal going by. This is a coal burning power plant. And with this capture unit, they could capture 5,000 tons of CO2 per day, has been demonstrated. And so that is an enormous capture unit. And what's going on inside there is they're removing CO2 from this exhaust stream coming off of the coal plant. And for a coal-fired plant, here's the mixture of molecules. The temperature they're treating, they have to cool, which costs a lot of energy. They're cooling the exhaust stream down to 40 or 50 degrees C. And they have to cool because the amines we're going to use to capture CO2 don't work at higher temperatures. But the total pressure is 1 bar, or 1 atmosphere of pressure. And the molecules in the stream are primarily nitrogen, 15% CO2. It's saturated with water vapor and a little bit of oxygen left over from combustion. And so as a chemist, you need to understand, how do I grab just carbon dioxide out of this mixture? And the way to do it is take advantage of the fact that CO2 is acidic, whereas the other molecules are not. And so this is what's going on in that giant tower in the Petronova power plant capture unit. You're taking an organic solution, so an aqueous solution of some organic amine, a molecule like monoethanolamine, and two of these organic amine groups will capture one CO2 molecule by becoming an ammonium carbamate. And this works very well. But this is not cooperative. And so the response of these solutions is a Langmuir type of adsorption behavior. It means that once you saturate that solution and want to desorb CO2 and use it again, you have to drive to extremely high temperatures, and there's a huge energy penalty for doing that. So we were interested in doing better. And one piece of inspiration we could take is from this ubiquitous enzyme, Rubisco. So Rubisco is an amazing and incredibly important molecule to life that captures carbon dioxide out of the atmosphere, a very dilute mixture, and brings carbon into the Calvin cycle. And the way it does it is buried within this enzyme is a magnesium site. And that magnesium site is surrounded by 5 oxygen donor ligands. And there's a proximal base. And the carbon dioxide will bind between the magnesium and the base. And if you replace magnesium with other metals, this no longer captures CO2 from air. So we can build a similar site into a metal organic framework in a 2-step reaction scheme. First, we're going to make a MOF. Making MOFs is pretty straightforward. You take a metal salt, some organic linker, mix them in a polar solvent, heat it up, and the crystals will grow at the bottom of your flask if you're lucky. So here we're reacting this magnesium salt with this organic linker. We've got 2 hydroxyl groups and 2 carboxylic acids. That linker will be deprotonated 4 times, and that 4- anion will stitch the magnesium cations together to form a honeycomb type structure. So at the right, you're looking down the channels in the honeycomb. These channels are about 18 angstroms across. And I want you to have a good idea of what a MOF structure looks like. This is from a crystal structure determination. But imagine you're a molecule of CO2 and you're flying towards a crystal of this MOF. As you approach the crystal, you can enter one of the channels, and this would be your view. So here you're flying down a channel, and the green spheres that you see are magnesium centers. And initially, those magnesium centers had solvent bound, but we can evacuate that solvent and expose the metal. To capture CO2 in this material, what we're going to do, is we're going to attach a diamine to every magnesium site that you're seeing in this channel. And importantly, the magnesium centers in green are spaced 6.5 angstroms apart as you go down the channel. So in this material, all those rows of magnesium cations, each will have a diamine, like ethylene diamine, attached. And so here in this example, we'll attach dimethyl ethylene diamine. And what's going to happen is we can capture CO2 between the magnesium and the bound amine. And so the response in terms of CO2 pressure is very nice. You see a steep uptake at low pressures, well below the concentration of CO2 in a flue gas, under flue gas conditions. And this is about 18 weight% CO2 uptake in the materials. So very high uptake of CO2 under these conditions. So this is very much a functional model of Rubisco, because the same thing is happening locally. We're getting CO2 inserting between the magnesium and the base. And indeed, this MOF can capture CO2 directly from air, where it's 420 parts per million in concentration. But this has something that Rubisco does not. Rubisco does not bind CO2 cooperatively. It turns out the MOF does. So if you look at the very low pressure region of these adsorption isotherms, for the first time, we have a material that doesn't have a Langmuir response to CO2 under these conditions. These are sharp, step-shaped isotherms, and nobody had ever seen that. And it took us quite a while to figure out exactly how it was working, but I'll show you the results. If you model these steps with the Hill equation that I showed, you get n equals 11. That means on average it takes 11 CO2 molecules all together reacting to drive the reaction forward and make a product. And the product that you're making is a one-dimensional chain of ammonium carbamate that's running along the rows of magnesium with diamines bound along the channels. And so here you're seeing a slice. This is from crystal structures. You're seeing a slice along the side view along the row of metal centers. So this is zinc instead of magnesium for growing large crystals. But each zinc has a diamine. The top structure is before CO2 adsorption. Bottom structure is after CO2 adsorption. So we got very lucky. The diamines are spaced just the right distance apart to form this one-dimensional ammonium carbamate chain. It means the first reaction site will actually lower the energy of the second and the third and the fourth and the fifth, and you get a chain reaction to form this polymer. And so very much like hemoglobin, this MOF will go and suddenly, at a very specific pressure and temperature, fill up with CO2, taking all those diamines to form ammonium carbamate chains. And so this is a breathing type of mechanism selected for CO2, very much like hemoglobin, but with a much higher degree of cooperativity. And you can see there's a gap down the middle of each channel for rapid incoming and outgoing gas transport. Okay, so just to reiterate the advantage here, these MOFs have a big advantage because you can do a regeneration step, desorption of pure CO2, putting in a lot less energy, a lot less of a temperature increase to give you the full capacity of the material. Okay, so the reason chemists are so interested in the mechanism is you want to control the properties. We want to control at what concentration does this thing turn on and suddenly fill up with CO2. We can use that mechanistic understanding to create adsorbents where we position this step, the sudden onset uptake of CO2, anywhere we want in temperature and pressure almost. And so there are lots of handles you can turn just by changing the diamine in this very inexpensive magnesium form of the MOF. So here are some examples, but we've put more than 80, probably 100 different diamines into that magnesium MOF. And at, say, 40 degrees C, you can move the step anywhere from very low pressures, 2 parts per million, where you're capturing very deeply from air, to very higher pressures, out past 2 bar, which might be of use for high pressure separation. And so if we take and think about the thermodynamics here that's moving the step, this is 13 different diamines in the same magnesium MOF that I showed you. So each point here is a different diamine. And what I plotted is along the horizontal axis is enthalpy of the reaction with CO2, vertical axis is entropy. And what you can see is we can adjust the enthalpy of that reaction anywhere from minus 40 kilojoules per mole to out past minus 100 kilojoules per mole. But as you go to stronger and stronger enthalpy contributions to the driving force, you're making more and more tightly held chains, and you're paying a larger and larger entropy penalty. And so we're falling along this gray master line. And it means you can choose a diamine to create an adsorbent to customize it to a particular gas mixture. And so if you're treating coal flue gas, like in the Petronova power plant, you've got 0.15 bar of CO2. And if you want to capture 90% of that carbon dioxide, then you've got to have your step at 0.015 bar or lower. And so that's going to minimize the temperature swing we need to do to regenerate and release the carbon dioxide. So for coal, capturing from a coal exhaust gas at 40 degrees C, we would choose that particular diamine. And then we can study what happens when we adsorb and desorb CO2 1,000 times. This is the last 200 cycles. Here we're adsorbing at 40 degrees C from a simulated coal flue gas, and then releasing at just 100 degrees C. And you're not seeing any degradation of performance in this experiment. So this is at 40 degrees C capture, which is standard for aqueous amines. There's a big advantage if you can capture at higher temperatures. You don't have to put all this energy into cooling the exhaust gas coming off at enormous rate from these power plants or from other combustion sources. We'd like to be able to capture at much higher temperatures so we don't have to do cooling, and also so we don't have to worry about co-adsorbing as much water on our sample. And so to try and get there, we started thinking about what can we do to capture at these higher temperatures. And one of the problems you face is when you go to higher and higher temperatures, even if you have the driving force to capture CO2, diamines can start volatilizing and coming off. And that's going to be, they're going to need to be replenished. That's an environmental problem. So how can we avoid that? We came up with the idea that let's make a tetramine where we covalently tether 2 diamines in a way that should still allow the polymerization reaction with CO2. And so here's one of the examples of a tetramine that we thought should work. And in fact, if you load them off with those tetramines, they organize themselves and you can get a crystal structure. And so there you can see the rows of tetramines. The tetramine has 2 binding sites now instead of just 1. And so they're much less volatile, and we can now go to several hundred degrees C without losing any of the amines in this material. And it does cooperative CO2 uptake now by design at high temperature. So here we're capturing at 100 degrees C and desorbing at 180 without any loss of capacity. So that made us curious, could we just direct steam contact these? So a lot of power plants, you could have some source of steam, and steam stripping could be a very effective way of regenerating and releasing the CO2. So these are robust to direct contact, which is very aggressive to expose materials to. So here's a little movie of what's going on in this tetramine MOF. We're going to look down one of the channels in the crystal structure. This is going to rotate 90 degrees, and you'll be looking down on rows of tetramines. And one thing to note is that CO2 is going to polymerize at two slightly different energies at each end of the tetramine rows. And so instead of a single step, we have a double step for CO2 absorption. Once you've loaded with CO2, you can bring in steam, release the CO2, and start again. Okay, so being able to tune these adsorbents and adjust the step position means we can make materials that are optimized for all kinds of places where we either are doing CO2 separations or should be doing CO2 separations immediately. And so, of course, flue gases, we're really not slowing down at all. We're putting more and more CO2 into our atmosphere at an alarming rate. But coal and natural gas power plants have different concentrations of CO2 in their exhaust, and you would choose a different diamine. Capture from air, capture from natural gas, biogas upgrading, life support, hydrogen production, all of these are different concentrations and would be a different adsorbent. So the PhD student who discovered these materials was Tom McDonald. And at the end of his PhD, he realized, we all, academics, we publish papers, and that paper's in a journal, and a few people will read it if you're lucky. And then nothing happens. There's no subsequent development of an actual technology. And so he decided that this wasn't going to happen unless he led it, and he thought it would be an important step for CO2 separations. So we started Mosaic Materials in 2018, or actually a couple years before that, and it's started working. The thing that they worked on was scale up. How do you make these materials at large scale, something that's scalable to many tons? And then how do you make them in shaped, mechanically robust forms, so pellets or stable films? So at the right, you're seeing an attrition test where you're bashing around pellets of the MOF. And then you get to a point where, yeah, we can scale these. They're looking effective at small scale for CO2 separations. If we want to go the next step, you've got two major problems. If you want to go to the next step, you need two things. You need a lot of engineers who know how to scale technology like this, and you need very deep pockets. Imagine trying to capture from a power plant. And we didn't have either of those things. And so instead of building it to move fast, we found what we thought was the best partner to come in and buy Mosaic Materials, and that's Baker Hughes. Baker Hughes is a huge global engineering company. One of their major products are gas turbines used in the oil and gas industry. And they have 5,000 gas turbines deployed worldwide, and they're spitting out unbelievable amounts of CO2. Data centers, our lives are being taken over by AI. Almost all those data centers are running off of turbines of the type that Baker Hughes makes. And that's potentially gonna destroy our planet. So Baker Hughes is interested in what can we put on the back of these turbines to stop CO2 increase in the atmosphere. But they started out, the scale of CO2 capture from one of those turbines is enormous. An easier place, a modular place to start could be trying to capture directly from air, which is the hardest CO2 separation because it's very dilute concentration of CO2. So Baker Hughes knows how to move and scale fast. So if you're like Randall here making compounds in the lab, actually he does work at some pretty large scales, but we're talking about grams and right. So yeah, we work with usually milligrams of compounds in the end to start, and then if we're ambitious, maybe 100 grams of a compound that would be a lot. But they showed they could make 2.5 tons at a time. And what you're seeing on the left here, that's not spaghetti, that's MOF extrudate. So this is extrudate is the precursor to the pelletized form of the MOF, and a lot of technology goes into developing that kind of thing. In the middle is a bucket of MOF pellets, and at the right is a cartridge that holds 50 kilograms of MOF, and 10 of those went into a couple of devices that have been tested now in Houston. So this is, again, capturing CO2 directly from air. Unfortunately, something that we need to do now because of CO2 buildup. Okay, so I'm going to switch now. I'll come back to CO2 in a minute, but I'm going to switch now to the idea that we might try to separate other molecules that are of importance in industry using these kinds of behavior. So here are some examples of important molecules we might want to capture cooperatively. This is a design challenge, a puzzle. How do you get one of these molecules to be selective in binding to the surface? And for cooperativity, you want it to be such that when one molecule binds, it lowers the energy for another to bind and another, and you want that to propagate through the structure. Right, so these are all chemical puzzles. Nature can do oxygen and hemoglobin. Nobody knows how to do cooperative O2 adsorption at high density. If you do that, you'll change the way O2 is produced from air. We've been successful now, first of all, with carbon monoxide, and this was intentional. And if you think about CO or any of these molecules, they're not acidic like carbon dioxide. So we can't use this acid-base chemistry that we've been using. You have to think of a new mechanism to get selectivity. And the famous thing about carbon monoxide that all inorganic chemists learned very early is it's a strong field ligand. It likes to stabilize low spin electron configurations on open shell transition metals. And so we took advantage of that and designed a MOF, again a honeycomb type MOF, that has rows of iron 2 centers with an open coordination site. And the iron 2 is high spin, but when it binds CO, it goes low spin. And that spin transition is selective for CO. Other molecules aren't strong enough field ligand to drive the iron low spin. And so here's the first nice step for carbon monoxide adsorption under these kinds of conditions. And so again, what happens here is iron binds CO. When it goes from high spin to low spin, the iron contracts in radius. That destabilizes neighboring irons. They also want to contract. They also want to bind CO. So it's an all or nothing proposition. You're either binding CO and going low spin, or you're not. This is just coincidence, but if you model that step, you again, with the Hill equation, you again get an exponent of n equals 11. Ammonia, we've recently shown we can do ammonia. Ammonia, the way to get selectivity is ammonia is a great ligand for metals, and it will displace things like carboxylate on copper. And so here's a very high capacity stepped uptake of ammonia into this material. And now with the Hill model, we get n equals 10. Okay, so let me switch gears a bit here and transition to going to even more extreme temperatures. And there are a lot of reasons you might want to do even higher temperature CO2 capture. For example, there are parts of our industry that are going to be very hard to decarbonize. They require very high quality heat. And examples of those are steel making and cement manufacturing. And those have exhaust gases that are on the order of 200 to 300 degrees C. You'd rather not have to put all the energy into cooling. Your cement or steel will be much more expensive. So the question is, can we capture at 200 or 300 degrees C? And how could we do that? And so we can take a blast furnace gas from steel production as an example. So in producing steel, you're reducing iron oxide with carbon monoxide and creating CO2 and iron. That CO2 then winds up in an exhaust gas that has this composition, and it can be much higher in temperature, but above 200 degrees C. It starts out much higher, of course. So here we've got nitrogen, CO2, CO, and water. You'd like to grab CO2 so it doesn't go and warm our planet. You'd like to grab carbon monoxide so that you could reuse it in making more steel. You really don't want to just burn these or exhaust them. So how could we do that without cooling? If we can do it hot, we can even feed hot CO back into the reactor. So can we capture CO2 and CO at these high temperatures? If you look at porous solids, there's nothing that CO2 sticks to at 200 plus degrees, right? If you want to grab CO2 chemically, you're going to need a reactive oxide, a material oxide. This is a dense compound. Those oxide anions will react with CO2 to make a carbonate. And that works, but it's very slow because you make a layer and more CO2 can't penetrate. And also, when you desorb CO2, you have to go to extremely high temperatures to get an appreciable rate of loss of CO2. There's no porous solids in this window of 2 to 300 degrees C. So we learned we could make one by taking advantage of some known molecular coordination chemistry. And we're going to start off with what's now my new favorite MOF. You probably don't have a favorite MOF, but I encourage you to consider this one. This is called MFU4L. We're not very creative in figuring out names for MOFs, but this is a MOF that was discovered in a lab in Ulm, Germany. And it's built up of not carboxylate or oxo-based linkers, but triazolate-based linkers. And it forms a cubic porous structure that's very high surface area, so 4,000 meters squared per gram. And if you look at the cluster nodes that are connected through these ditriazolate linkers, you have something that looks like this. This is called a Kuratowski cluster. And in this structure, you've got an octahedral zinc in the center, and then 4 peripheral zincs with a terminal chloride. And those peripheral zinc sites look very much like a simple tris-perazoyl borate coordination complex with a tetrahedral zinc chloride. And so we can make an analogy here, and the chemistry that can happen with tris-perazoyl borate compounds, there's a huge range of reaction chemistry that's been explored in solution. We can transfer that now to isolated sites reacting within a MOF on incoming gases. And one reaction that these kinds of molecules can do is if you replace the chloride with a hydride, that hydride will sluggishly react with CO2 to make formate. Right? And the reverse hadn't been shown, but you can see it takes quite a while to make the formate. Well, we can make this in a MOF. So first step, we're going to replace the chloride with formate, which is just a ligand substitution, and here's the crystal structure. And then if you heat that formate, you can release CO2 and make the hydride. And here's the structure of the hydride. You can see that short 1.5 angstrom zinc hydrogen bond distance. And if you make this in the hydride form, it has, again, very high surface area. It's incredibly unusual in that it's a hydride, it's a metal hydride that you can put on your bench top, and it doesn't react with water or oxygen. So that's not, for those of you who are chemists working with metal hydrides, a lot of them are very sensitive. A lot of the ones you use in your reactions, you don't bring out onto your bench top. But this can be set, you can sit it on your bench top for 2 years, and there's no loss of the hydride, no degradation. You can heat it in oxygen 300, and the reason it's not hydrolyzing, reacting with water, is that it's a sterically protected zinc hydride site. Right? And you can see there are 3 CH bonds surrounding the zinc hydride in a triangle, and that hydride is deep in the pocket in the corner of the MOF pore, and it creates a large activation barrier for reaction with CO2. If you take gas adsorption data, here's the result. Probably none of you are often looking at adsorption isotherms like this, but this is the most stunning gas adsorption data I've seen because of the temperature. 300 degrees C, huge uptake of CO2, it's fully reversible. So the filled circles in these plots are adsorption, where we're increasing the pressure. Open circles are desorption, decreasing the pressure. This is showing this huge capacity for taking up CO2 at 300 degrees C. It's never been seen before in a porous material. But you can just use vacuum to swing the CO2 off. So normally CO2 in a solid, like physisorption, it's going to be like the other gases at the very bottom. There's no uptake. At 300 degrees C, you have a huge entropy penalty. The heat means the molecules want to be in the gas phase. And what's happening is at high temperature, we're overcoming a reaction barrier and we're making the formate. And the thermodynamics are such that it wants to bind at 300 degrees C. And part of that is the entropy. So if we think about all these amine-based adsorbents, the organic amines have lots of degrees of freedom. They react with CO2, they make an ammonium carbamate that locks into position. So you're losing lots of freedom in the molecules when you do the reaction. Delta S is large. With the hydride, the zinc hydride has very few degrees of freedom before CO2 capture. So delta S for this reaction is much, much smaller. And that's why this material can operate at high temperatures. So here's the calculated reaction profile. We're going over this large barrier of about 120 kilojoules per mole. And we're forming the formate. It's, and at 300 degrees C, you can go over and back profile, and you can operate at equilibrium. And you can see in the transition state, the hydride is attacking the carbon and it's being pushed against the CH bond, creating that barrier. Okay, so now we can capture at these high temperatures and we can cycle without changing the temperature, just with a pressure swing. Right? This can be very fast. It's much better than you can do with magnesium oxide. You can cycle these so fast, you can do a 60-second cycle, adsorption and desorption, and get a large productivity for CO2 removal at 300 degrees C. Okay, briefly, let's come to carbon monoxide. We also have high temperature carbon monoxide we'd like to capture. And to do that, we want to get to something that's really a very good pi donor. So one thing CO can do is make really strong pi bonds with the metal. And a great metal for doing that is copper-1. Copper-1 has two electrons, two orbitals to make pi interactions with CO that are filled. And so this should, copper-1 sites, if we can replace the zinc chloride with copper-1, which we can by this reaction, you create a pyramidal copper-1 site with an open face for coordinating CO. Sadly, we can only get about 2 to 3 of these coppers exchanged in this reaction, instead of all 4 of the peripheral sites. But this material now binds CO at very high temperatures, near 300 degrees C here. And you can see it's reversible just with vacuum swing. It also has an appreciable affinity for ethylene. You can see ethylene is the next steepest isotherm, which is also very difficult at these temperatures. Okay, and you can adsorb and desorb using a vacuum swing. Last thing on these MOFs for gas separations. Can we make MFU4L behave in a cooperative way? Can we create a step in these materials? We don't have chains of metals. We have 4 per tetrahedral cluster. there is one way we can do that to start, and it happens if we make the methyl, first we replace zinc with cobalt, then we replace chloride with a methyl group, and that cobalt methyl group for tris-perazoyl borate complexes was known to react with two CO molecules reversibly. We can do the same thing in the MOF and create a very high capacity where every cobalt with a methyl grabs not one but two CO molecules. You double your capacity per metal. And if you look at this adsorption data in a log plot, it's not a Langmuir isotherm. It has a shallow step. And that's because the first molecule of CO that binds the cobalt, it creates a 5-coordinate cobalt that's low spin. And then the second CO binds at an even stronger binding energy. And so this is now site selective or single site cooperativity for the first time in a porous material. And so Hill exponent here is 2, as you'd expect for the reaction. Okay, I'm going to go very briefly into this because I know I'm out of time. So I mentioned at the beginning, we work also on these amorphous porous network polymers called PAFs. And the way you do a coupling reaction with something like this brominated tetraphenyl methane, and ideally this would grow making carbon-carbon bonds to a beautiful diamondoid network. But the irreversibility of this coupling reaction means that we don't get a nice crystalline network. Instead, we get an amorphous network. But it has a huge surface area. This is built up only of strong carbon-carbon bonds in the backbone of the framework. 5,000 meters squared per gram. This is better than most of our MOFs. And importantly, these are robust to very strong acids and very strong bases. So 12 molar conditions, no problem. So the idea is that we can chemically functionalize the biphenyl struts within this network and attach binding groups that could be selective for metal ions. And so we can put in, depending on chemistry, groups that target a specific metal ion that might be present at very low concentrations in a broad mixture of metals in solution. And so we've put many different functional groups at high and varying densities within these materials. Some of them are shown here. And you want to target your binding properties with the properties of the metal. Hard, soft character of the metal, electronic structure, electron donation or receiving ability. Radius is very important, and charge density. And so we got into this area by trying to remove toxic impurities from water sources, drinking water, water for agriculture. Polyols on the surface, then we can grab chromium and arsenic at very low concentrations, 2 different mechanisms. With chromium, we're doing a redox reaction and reducing the chromium to bind it as shown. With arsenic, we've got a mixture of charge interactions and hydrogen bonding going on. But the place where this could also be impactful is in recycling metals from all of our technology, all of our weapons, and mining those metals as well. So this brings us to critical elements. I'm sure you use a lot of them here. We use them for all of our technology, essentially. And very few of them, almost none of them, unfortunately, are produced in the US. So we're reliant on other countries being willing to sell us these metals. And so your cell phone has a huge number of different elements in it. Eventually, it's going to no longer be useful to you. And you'd like to recover those metals instead of mining new metals for building a new cell phone. So how can we recycle the metals from your laptop, from your solar panels, from your cell phone, from your iPhone, from any of your devices. So here's a Samsung Galaxy. I was at Samsung a couple weeks ago, but there's extraordinary range of metals. And to get at those metals, you're going to take some components and you're going to dissolve them in strong acid. And you're going to get a very strong acidic solution with potentially dozens of different metals in it at different concentrations. So we need to build adsorbents that can target very selectively a single metal and pull it out of that solution and spit it out in pure form for reuse. And that's what we're trying to do with these paths. Okay, so one of the hardest problems is lanthanides. Rare earth elements are very very expensive, not because they're not abundant, but because they're very difficult to separate from each other. You have to do hundreds and hundreds of steps. And it's currently done mainly by solution extraction, where you've got an organic layer or component that has ligands that will pull lanthanides or rare earths into that organic phase. And it does that with a very slight selectivity based on charge density of the rare earth. But the selectivity is extremely poor, and you have to do this many, many times to get a pure lanthanide or rare earth. And you'll note that these ligands, it's the phosphonate groups that are selective, these very hard donors that are binding the hard rare earth cations. And we'd like to do this at low pH because if we have to raise the pH a lot, that's a lot of waste chemical that you're pouring in. So we functionalized our paths with phosphonate ligands, and you want more than one phosphonate to be able to bind the cation. So there's two ways we approach this. One is we attached multi-phosphonate containing groups on the biphenyl in path 1. Or we can make a different path with terphenyl struts that actually forms an interwoven or interpenetrated network structure. And then monophosphonate groups from different networks can bind a single metal. Both of those strategies work. And it turns out two of these materials are incredibly selective for scandium. So scandium is one of the rare earth metals, and it's the most charge dense one. So scandium 3+, you can see all the other metals here. This particular path, if you have a mixture, it just grabs scandium. And it's selective for scandium, extremely selective over other lanthanides, so here, the vertical axis is selectivity over lanthanum 3+. Horizontal axis is scandium uptake. The best adsorbent will be at the top right quadrant. And the two polymers that I just showed you are at the very top in terms of selectivity. Also, selectivity over iron is important for scandium recovery. Again, those two polymers are at the top right. If you're going to use these, the best way to do this for getting fast contact with the metals is in a fluidized bed instead of a fixed bed where the particles of the polymer are fixed. We're going to suspend the particles in a fluid in the incoming water stream, aqueous acid, and they're going to capture. This is a breakthrough curve. This is just showing that only scandium will stick to that column or that material in the fluidized bed. Everything else that we tested comes through. We can release scandium. Once we've saturated, we can release scandium just by changing the pH. A pH swing releases the scandium, and then you can use the adsorbent again. We've tested this on scandium-containing minerals. So laterite ores are a type of soil with iron, large iron and aluminum content. Monazite is a source of lanthanide and scandium rare earth elements. And here we're showing selectivity. Once you've grabbed scandium from those mining samples, these are real samples from a mine. You can then take and do a pH swing, and then calcination gets you to very high purity scandium oxide, which is the form it's usually sourced in and shipped in. Once you've removed scandium from those solutions, those adsorbents will next go after the highest charge density lanthanides. So you can start to pick them off, and lutetium 3+, we've got quite good selectivity here. It's much better selectivity than the organic molecules in solution, in part because there's rigidity. The phosphonates in our material are much more rigid than those ligands in solution that are free to move. You can get much better size selectivity for metal binding if you have a rigid capture pocket. I won't go through this, but we can extract germanium from semiconductor waste, copper from spent solar panels, precious metals using sulfur-based ligands. We can separate all 6 of these precious metals one by one using different paths. And so we're working on getting selective adsorbents that can really attack each of these metals that are needed for technology and potentially for mining. And so the advantages here, just to summarize, we can use molecular chemistry to build in selectivity for our target metal, and we can have a high capacity owing to these high surface areas. This can minimize water use and energy use for separation because it could be very few steps. And we don't have organic waste. We don't have a lot of the waste that's associated with hydrometallurgy, the current way we separate metals in mining. Okay, so, just last point. 2 former PhD students, Adam Liana and Ever Velasquez, started ChemFinity to scale up these materials and start using them for metal separations. They're starting with catalytic converter waste and recovering palladium and rhodium. Okay, let me thank some absolutely brilliant students, postdocs, collaborators, sources of funding, and thanks for your attention.
So in the beginning of your talk, when you were describing carbon capture from the coal power plants and like the legacy technology of just dissolved amines in solution, and the energy cost you said was around 30%, is that relative to the output of the coal plant?
Yeah, it means yes. You're going to have to generate 30%
Right.
energy to produce the same amount of electricity. Use 30% more coal to produce the same amount of electricity and capture CO2.
Huh? Oh.
Sorry about that. Is this on? Yeah. Yeah, so the 30% means that you're going to have to burn 30% more coal to produce the same amount of electricity while capturing the CO2.
Yeah, I was curious if you had a sense of the energy cost for, your best-in-class MOF. I know it's less, but I was curious if you had a sense of what it would be.
Yeah, that's a great question. Is this on? Yeah, it's a great question, and it's very hard to give you numbers, but because you have to really tie it to the process that you're designing, and the process you would use for doing the separation with a solid adsorbent is very different from those amine scrubbers, aqueous amines. Liquids minimize surface area. To do CO2 capture with a liquid, you have to build a contactor and do a trickle-down bed where you create a very thin layer of the solution so that you have reasonable kinetics. But we should be able to get maybe half of that if you do a comparison, which we've done. There are some variables that we don't know very well, like true lifetime. It takes a long time to demonstrate what's the true lifetime on a coal flue gas, because there's other stuff in that exhaust gas. And so with some speculation, we could maybe get it down to 15%. But there's some numbers there that we don't really know. And we know them better for, say, air capture and natural gas combined cycle exhaust gas. We've not really gone after coal. Hopefully we'll stop using coal, although it's looking like we're going the other direction now. But and here now, well, we're going back to bringing on more coal. Other questions?
Really good talk. For your PAFs versus your MOFs, it looks like you've got a much more tortuous pathway. How does that affect capacity, or does it?
Capacity is really linked to thermodynamics rather than kinetics. So what tortuosity would more impact would be the uptake kinetics, how fast molecules can find a binding site. But these, and it will make a difference in kinetics if you, particularly if you're making an adsorbent where the functional groups on the backbone of the material are crowding the pore and making diffusion barriers. And then tortuosity would be a limit, it would slow down the reaching capacity. So it's hard, it's going to be a hard thing, but we are going after how do we make PAFs crystalline? How do we reverse that coupling bond, CC bond formation and building them to get to crystalline materials? Then you have really perfect binding sites, not some variation in what your binding sites look like.
Thank you.
Have you ever observed a exponent for the Hill equation that exceeds 11, or do you think that could be like a empirical limit in practicality?
Yeah, we have. So there are two things I think at play here. When you change the diamine, it actually can vary all over the place. A lot of cases it's lower than 11, and if you do a shoddy job of making your MOF, then it could be really low. If you make the perfect material, it could be higher, but fundamentally there can be limitations, and it can be strain. The ammonium carbamate chain that you're building might not be a perfect fit for the 6.5 angstrom spacing in the MOF. So strain buildup may be contributing to how long those chains are before you have another chain segment.
I guess follow-up question, whenever you're desorbing the CO2 from these MOFs, where does it go? What do you do with it then?
Yeah, so CO2 capture, the places we need to do it, it's so much carbon dioxide, there's nothing you will ever do with it. And the only solution is injection underground and sequestration, hopefully in sites where it can remineralize before it finds its way back up. And so that technology is existing. Oil and gas companies know very well how to get gases in and out of the ground. In fact, they use CO2 for, if they can get hold of it, they use it for enhanced oil recovery. It's a great working fluid for pushing oil out of the ground. Once you've done that, you can cap off the well and the CO2, like the natural gas that's been under there for millions of years, the CO2 can stay. But you have to have really good geologists, and you can't make the mistake of doing all this to inject and then it comes back up. That would be a public relations nightmare.
Other questions? At lunchtime? Yeah, right here.
Hello, really cool talk.
Thanks.
I had a question on the second MOF that you showed with the pyrazole units. I was wondering how you, I know that in the synthesis of pyrazolines, you get these sort of like regioisomers. I was wondering how you're able to reduce that. From different works that I've seen, usually it's like something like 50-50. And I know that like stereospecificity is probably really important in this. And so I was wondering if there's like any techniques that you did to reduce that.
Yeah, you may not have been able to see as well this people up here. The MOFs I showed today were triazolate, so 1, 2, 3 triazole instead of pyrazole, and so the two carbons are equivalent. And the linkers I showed, though, actually had arene group, a benzene ring on attached to both of those carbons. So it went by fast, but yeah, there's that can be a problem for pyrazoles, and we have made dipyrazolate linked MOFs, and for making those linkers, you do have to worry about that kind of problem.
Cool. Thank you.
When you were synthesizing the copper substituted version of the MOFs with the triazolates, would it be possible to directly build the MOF from the copper chloride rather than trying to substitute it after getting the zinc version of the MOF?
Yeah, so a couple of things. We are trying to do that, but you don't. So there's a central octahedral metal in the middle of the node, which is also zinc, and if you put copper-2 there, the Jahn-Teller distortion is likely to distort. It does distort the node, and which is not great for stability. So you'd want to assemble something with, say, zinc in the middle, and then copper's on the periphery. That might be possible, though. So we are trying direct assembly ways of making that. I don't see any structural reason we shouldn't be able to get to 4 copper-1 sites, and that would boost capacity, and it's an important MOF not just for CO capture, as I showed, but actually it turns out that one reacts really nicely with oxygen and air. It forms the copper-2 superoxide, and so that's actually our best material for O2, separating O2 from air. So hopefully we can get there. Okay, looks like it's time for lunch.
Any other questions? All right. Well, with that, we'd like to thank Dr. Long with gratitude for your contribution as a distinguished lecturer. Thank you for your commitment to advancing innovation and the Navy Tech Connect mission to connect ideas, technologies, and people in support of the warfighter.
All right.
Thank you very much.
Thank you very much, everybody.
Thank you.